Okay, this is Unit 2 for Geometry A. It's called Compose and Decompose Shapes. I just call it the Shapes unit. It's going to start off with circles, so here we go. This is called a central angle. Okay, and if this is a central angle, it's congruent or has the same measure as the arc that it intercepts. So if this is 129 degrees, then from here to here is 129 degrees. But they're asking for the measure of arc CD, which is a minor arc. Okay, so from there to there. Now, if it was a major arc, there'd be 3 letters, and I'd know to go the long way, but this is the short way. And hopefully you notice, hey, half circle. Okay, so I'm going to go ahead and bust out a calculator here. And we're going to go 180, because you should all know a half a circle is 180 minus 129, and we get 51. So this, the measure of this arc is 51 degrees. Okay, next problem. Oh, I notice major arc. So it's going to start at T, shoot through C, and end at B. Now, I notice this is 90 degrees, which means this arc is 90 degrees. So 360 minus 90 is 270. That was a pretty easy one. Okay, next one. This is not a central angle. This is called an inscribed angle. And an inscribed angle is always half of the arc that it intercepts. So I'm going to do half of 127. So 63.5, that's going to be angle A. Angle B here, oh, let's do C here while we're at it. Because I notice if that's 127, and again, you notice we have a half circle. So let's do 180 minus 127. 180 minus 127 gives us 53. So this is 53 degrees. And then last but not least, let me erase some of this stuff. I'm looking for this angle. But hopefully you notice, well, there's no numbers associated with it, but this is the arc that intercepts. And if this is 180 degrees, then this has to be half of that, which is 90. And this will be all inscribed angles that intersect the diameter. All right, moving on to quadrilaterals. This is called a parallelogram. With these arrows, identify those 2 sides are parallel, these 2 sides are parallel. Okay, here's how parallelograms work. Opposite angles are equal, so if that's 63, that's 63. If that's x and that's x. But consecutive angles, like the orange and the blue one, are supplementary, so those have to add up to 180. So 180 minus 63 is 117. Okay, next problem. Okay, this is called an isosceles trapezoid. I can tell by these tick marks. Base angles here, just like an isosceles triangle, are going to be the same. So if that's 52, that's 52. And just like we did in the last problem, the parallelogram, because of these parallel lines, these consecutive angles are going to be supplementary. So that means angle 1 and 2 here have to add up to 180, and angle 3 and 52 have to add up 180. And angle 2 and 3 are also going to be equal. So let's do 180 minus 52, and we get 128. So 128 for both of these angles. 128, 128. Okay, this is called a trapezoid mid-segment. There's a little formula here I'm going to write up again in this problem. So the mid-segment is equal to 1/2 the average of the bases. So base 1 plus base 2. So I'm going to plug some things into this. So here's my mid-segment. That's going to go here. So let's put a 2x right here. I still have this 1/2. And I don't really care what your bases are. which is base 1 or base 2. Base 1, base 2. These can be flip-flop. It's not going to make a difference. And I get x plus 5 plus 22. Okay, let's clean this up a little bit. First thing I would do is I would get rid of this. I don't like this dividing by 2 here. So I'm going to multiply both sides by 2, and those go away. So on the left I get 4x. On the right, no more fraction. And I can also put these together. So I get x plus 27. All right, this is an algebra equation. Let's subtract x from both sides. And we get 3x equals 27. And now it's a division problem. Divide by 3. And we get x equals 9. Now be careful. You do got to plug it back in here. So I don't want just 9. It says, what is the measure of EF? So it's 2 times 9. So this answer right here should be 18. Okay, this is called a kite. One thing you need to know about kites is you notice those cross at 90 degrees. So angle 1, kites will always, their diagonals will always intersect at 90 degrees. Here's another easy part of this. You notice it is an upside down kite, but these two angles are congruent. So if the angle to the right is 53, then angle 3 is 53. And then I'm going to focus on this little triangle. All triangles add up to 180. So if I know that's 90 degrees, then those two other angles have to add up to 90. So let's go 90 minus 53, and that gives us 37, and that's angle 2. Okay, this is a pretty complex problem. There's a lot going on here. So I'm going to start off with these angles C and D inside of this quadrilateral. This is called a cyclic quadrilateral, and the rules here are opposite angles have to add up to 180. So those have to add up to 180, and these have to add up to 180. So let's do some quick math on the calculator. So 180 minus 99 is 81. So C is 81. 180 minus 108 is 72. So 81 and 72. So C is 81 and D is 72. Okay, now let's figure out what some of these angles are. And I think it has to do with inscribed angles. So I'm going to focus on this inscribed angle. Okay, so I notice from here to here, if that's inscribed, then the arc here that it intercepts has to be twice as big. And so this whole thing has to be 216. And if I know this sliver from here to here is 94, I'm going to do some basic subtraction. 216 minus 94 is 122. So A is 122. So I'm going to put that up here. A from here to here is 122. And let's put that over here. Okay. I'm probably going to focus on now this inscribed angle from here to here. Okay, so I notice this one, actually, no, let's go backwards. Let's fill in C here. So if I know that's 22, angle C was 81. I'll focus on this one, 81, excuse me. Okay, and then I can find B. So that means if I double 81 from here to here, that means this whole thing would have to be 162. And now I'm just going to subtract 122 from it, and I get 40. So my last angle, or arc here, arc B, is 40. Okay, let's move on. Okay, this is a little English and math class. These are called conditional statements. They all relate to proofs. I'm looking for the words if and then. So if and then. And what follows if is called um, our P, and what follows then is called our Q. So this is called our hypothesis. Excuse me, I don't know why they use P's and Q's. You might have to look it up or something. And this is called our Q. So a normal conditional statement is if P, then Q. Well, the converse of this is when I flip these. So I'm going to put Q first. I'll even color coordinate it. Q first, and I'm going to put P second. Okay, so I'm going to highlight these a little bit. So let's start off with something about a number square being positive. And I notice, oh, right there, number square is positive. This one has nothing to do with a square, so I don't like that. Oop, I like that one. And then this one says not positive. I don't like that. There's nothing up there about saying not positive. So it's either A or C so far. Now let's look at our P here. P has something to do about not just number being square, but the number is positive. Number is positive. Oop, don't like that. It says not positive. So it's got to be A. So that's our conditional statement. Okay, now if our original conditional statement, excuse me, that's our converse. If our original statement is true and our converse is true, then we can do what's called a biconditional statement. We're going to use, in the middle, we'll use the words IFF, if and only if. And I can see it a bunch of times up here. If and only if and only if and only if. Almost all of them have it, okay? And all I would do if I did that is I would get rid of this part here, and I would get rid of this part here, and I would put in the middle, if and only if. Now, this is only if it's true. So let's see if this is true. I'm testing the validity of this statement. If a square number is positive, then the number, if the square of a number is positive, then the number has to be positive. So let's think of that. So here's the square of a number. Does it mean the number I squared right here has to be positive? And that is not true, because hopefully you know you can also square negative numbers, and this would also work. So the converse is false here. No conditional statement. Okay, question 10. This is called an isosceles triangle here, and that means base angles have to be the same. And we know all triangles add up to 180, so let me get my calculator out. So 180 minus 50 is 130. So those two angles have to add up to 130, and they have to be the same. So let's divide 130 by 2, and we get 65. So both those angles there have to be 65. Okay, this is called exterior angle of the triangle. Here's an easy way to get this, okay? Those two, what are called remote interior angles, have to add up to that exterior angle. So 45 plus 46 is 91. So angle 3 here has to be 91. And this is called a linear pair. So those have to add up to 180. So 180 minus 91 is 89. So this has to be 89. Okay, let's move on to these next problems. Okay, this problem. These are called triangle midsegments. So if this is a midpoint and midpoint, then this midsegment is half of the base. Same thing here. Midpoint, midpoint, midsegment, half of that base. And last but not least, if these are midpoints, then this has to be half of this. Now, I'm going to look what they're looking for. HE, that's this one. So I really like to know this length. The rest of the lengths don't matter to me. Okay? And I look up there and I notice, hey, U to V is 94. Well, what's half of 94? 94 divided by 2 is 47. So that means H to E is 47. Okay, this is called the circumcenter of a triangle. It's made by perpendicular bisectors. So I'm going to go ahead, I'm going to find the midpoint of this top horizontal line. So right in the middle there, and I'm going to make a line that's perpendicular, like that. I'm going to do the same thing over here. Okay, midpoint is right there. I'm going to make a line that's perpendicular to that. It's very convenient when we have right triangles that have horizontal and vertical lines. This is my circumcenter, okay? And so I notice that is -3, -5. Okay, what is a circumcenter used for? Why is it helpful? Well, if this is drawn to scale, we'll do a quick check to see if it is. This will create a circle, which is basically a circle around. So if I were to put this down, and I'll put it out here, that looks pretty good. And oh, look at that, drawn to scale. Nice. Not that you need to do that, but okay, this is called an incenter. I can tell because these are angle bisectors, angle bisectors. Okay, now this would make a circle inside. I can already tell this isn't to scale because those don't all three look. But basically, we would draw a circle on the inside. But all I care about is those have to be the same length. So if I were to do some algebra here, 2x minus 3 has to equal 7x minus 23. All right, let's move our x's to one side. And while we're at it, let's go ahead and move our whole numbers together. So I'm going to add 23 to both sides. Those go away, those go away. I get 20 equals 5x. Now it's a one-step algebra equation. And we get x equals 4. 4. Okay, last problem. This is called the centroid. Centroid is created by medians. Okay, if I go from the midpoint, if this is directly between those two parts of the segment to the opposite vertex, that's called a median. Same thing, midpoint to opposite vertex. Now, the way a median is broken up, okay, it's all about thirds. So if this whole length, the red length would be a third of the distance, and the blue length would be 2/3. So if this is 36 total, then the red portion would be 1/3 of that, which is 12. Now, the other thing I can think of is the blue section is twice as big. So if I double the small section, I get 24. And 12 over 36, we know, reduces to 1/3. And 24 over 36 reduces to 2/3. And done and done.